Welcome to Spaceverse, your portal to cosmic adventures. The much-anticipated results strongly back up the standard model of cosmology, though with a notable caveat. Data from the James Webb Space Telescope, gathered from 10 nearby galaxies, indicate that the long-debated Hubble tension, the puzzling mismatch in measurements of the universe's expansion rate, might not actually exist. According to Webb's observations, the Hubble constant, or H0, comes out to an average of 69.96 kilometers per second per megaparsec. In simpler terms, this means that for every megaparsec, which equals 1 million parsecs, or about 3.26 million light-years, the fabric of the universe stretches by almost 70 kilometers each second. This figure is consistent with predictions made by the standard model of cosmology, which seems like it should close the case on this long-running mystery. But the truth, as always in science, is a little more complicated. Because while Webb's results line up nicely with expectations, they also highlight a deeper and persistent disagreement. Let's rewind for a moment to 2013. That year, the European Space Agency's Planck mission, which studied the universe's oldest light, the cosmic microwave background, or CMB, came up with a very precise measurement of the Hubble constant. According to Planck, H0 should be 67.4 kilometers per second per megaparsec. This measurement was made by carefully analyzing the CMB, then applying the equations of the standard cosmological model to predict the expansion rate. And here's the key point. If the model is correct, this method should be accurate to within 1%. That sounds ironclad. But then came another method, one that seemed to tell a different story. A team led by Adam Rees of Johns Hopkins University used the Hubble Space Telescope to measure the expansion rate in a more direct way, using Type 1, supernovas, the catastrophic explosions of white dwarf stars. These cosmic explosions are extremely useful because they have a standardizable brightness. In other words, astronomers can tell how far away a Type 1, supernova is by comparing its true brightness with how bright it looks from Earth. Once the distance is calculated, it can be compared with the object's redshift, the stretching of light waves caused by the expansion of space itself. The faster the universe expands, the greater the redshift. Using this technique, Rees and his colleagues came up with a value of 73.2 kilometers per second per megaparsec. That's noticeably higher than the Planck value and suggested that the universe is expanding faster than the standard model predicts. This discrepancy is what scientists call the Hubble tension, and for the last decade, it has been one of the most puzzling problems in modern cosmology. And that brings us to the new work led by Wendy Friedman of the University of Chicago. Friedman's team is behind a project called the Chicago Carnegie Hubble Program, or CCHP. With the James Webb Space Telescope's unmatched infrared vision, they set out to measure the distances to 10 relatively nearby galaxies. Importantly, each of these galaxies had been observed to host a Type 1, supernova. To ensure accuracy, the team cross-checked their distance measurements using 3 different, independent methods. The first method is known as the tip of the red giant branch, or TRGB. This technique takes advantage of the fact that evolved, sun-like stars known as red giants can only get so bright before reaching a limit. That maximum brightness can be used as a sort of cosmic yardstick. The second method involves a special group of carbon-rich stars known as the J-region asymptotic giant branch stars. These stars have a very stable intrinsic brightness in the infrared, making them reliable markers for measuring distance. And finally, there are Cepheid variable stars. These stars pulsate in brightness in a predictable way, and the period of their pulsation directly correlates to their luminosity. This relationship, first discovered in 1908 by Henrietta Swan-Leavitt, is a cornerstone of the so-called cosmic distance ladder. By timing the pulsations of a Cepheid, astronomers can determine how bright it truly is, and then compare that with how bright it appears to us to figure out its distance. So, what did Friedman's team find? Using the tip of the red giant branch, they measured H0 as 69.85 kilometers per second per megaparsec. Using the carbon stars, they came up with 67.96 kilometers per second per megaparsec. So far, so good. Both of these results overlap with the Planck measurement once error bars are accounted for. That means they're in solid agreement with the standard model. But then came the Cepheids. The value obtained from them was 72.04 kilometers per second per megaparsec. That's much closer to the Rees group's supernova measurement, and not in agreement with the other 2 methods. When all 4 methods were averaged together, the the result came to 69.96 kilometers per second per megaparsec. Friedman summarized the findings this way. Based on these new JWST data and using 3 independent methods, we do not find strong evidence for a Hubble tension. To the contrary, it looks like our standard cosmological model for explaining the evolution of the universe is holding up. So does that mean the Hubble tension is officially solved? Not exactly. The Cepheid variable measurements are still presenting a problem. And since Cepheids form the bottom rung of the cosmic distance ladder, with Type 1a supernovas as the next rung, this is no small issue. In fact, Rees's team relies heavily on Cepheids to calibrate their supernova measurements. If Cepheids are giving misleading results, then the supernova-based expansion rate might be skewed as well. Friedman has pointed out a potential problem called crowding. The Hubble Space Telescope, while incredibly powerful, might not always fully separate a Cepheid from nearby faint stars. If those nearby stars blend into the Cepheids' light, it could artificially inflate its measured brightness, making it seem closer than it really is. Earlier this year, Rees and his colleagues used the James Webb Space Telescope to recheck Hubble's Cepheid measurements. Their conclusion? Crowding wasn't an issue. But Friedman and her team argue that the 2 methods least affected by crowding, TRGB and the carbon stars, are the ones that line up best with the Planck results and the standard model. This debate is far from over. What happens next will largely depend on further measurements. Ideally, astronomers need more galaxies that contain all 3 of these stellar markers, Cepheids, red giants, and carbon stars, as well as a Type 1a supernova. That way, they can directly compare results across the board. The problem is that such galaxies are relatively rare, which means building up a big enough sample will take time. Still, the early results from JWST are promising. They suggest that the Hubble tension might not be as severe as once thought, and that the standard cosmological model, which has successfully explained so much of our universe's history and structure, still holds strong. But at the same time, those stubborn Cepheids refuse to give us a simple answer. And maybe that's the real beauty of science. Every time we think we've tied up a mystery, the universe finds a way to keep us searching, questioning, and refining our understanding. The Hubble tension debate may continue for years, but one thing is certain. The James Webb Space Telescope has already reshaped the playing field. With its sharp infrared eyes, it is giving us clarity where before we had only blurry hints. And as more data pours in, we may finally learn whether the cosmos really is expanding faster than we thought, or whether the tension was simply an artifact of the tools we use to measure it. Either way, what we're seeing unfold is science in action. Bold claims tested, challenged, and retested until the truth gradually comes into focus. So, what do we make of all this? The James Webb Space Telescope may have given us the clearest picture yet of the universe's expansion, but the story of the Hubble tension is far from over. The answers are leaning toward the standard model holding strong, yet Cepheid variables continue to whisper that something might be amiss. It's a reminder that science is never static. Each observation, each new dataset, either reinforces what we know or pushes us to refine our understanding. And sometimes, it does both at once. As Webb continues its mission, measuring more galaxies and uncovering more cosmic markers, we'll move closer to finally settling this debate, or perhaps uncovering an even deeper mystery about the fabric of our universe. After all, that's the beauty of cosmology. Every answer leads to a new question. Thanks for joining us on this journey across space and time. If you enjoyed diving into this cosmic puzzle, don't forget to like, subscribe, and share this video with fellow space enthusiasts. And as always, keep your eyes on the stars, because the universe always has another secret waiting to be revealed.